Hey there, algebra students. Okay, we are going to talk about arithmetic sequences today, as well as the recursive rule for how to write the arithmetic sequence. Just so you know, a sequence is actually a special type of function. Specifically, it's a function where it's basically just a list of outputs, and those outputs are based on input values that are the natural number system. So that's probably above your pay grade as far as intellect goes, as far as what you've been taught. But the natural number system is just whole numbers or integers starting at 1, going on forever. So 1, 2, 3, 4, 5, 6, 7. So basically our inputs are 1, 2, 3, 4, 5, 6, 7, 8, 9, etc. And our outputs are the values of the sequence. So here I have it. You can press pause and take notes. A sequence is a list of outputs where the inputs of the function are natural numbers. And then there's an example of the natural number. So it always starts with the value 1. Okay? A subscript n names the sequence. Okay, so just so you guys know, this is like a little subscript, right? It's like underneath the A or attached underneath it, like how you have an exponent that's above it, except this is a subscript, not a superscript. Okay, so if you ever hear us say like a sub 5, we're not saying the word ace of 5. Okay, I have algebra students every year that get confused with that. It's a subscript 5, a sub 5. But for shorthand, we typically just say a5 or a7 or a sub 7 is the more mathematical way of saying it. But I'll just say it an, even though it's really a subscript n. Okay, an names the sequence, but it also means any term. Keep that in your notes. A subscript n means any term, okay? Or a specific term number that we're at, or the current term, okay? But put that in your notes, okay? For example, a1 or a subscript 1 means the first term. So 1 being the input value, and then the value of a1 being the output value, okay? So a1 means the first term, n equals 1, right? Because instead of it being an n there, it's a 1. So n equals 1. And whatever that happens to be, let's say it was 5, that would be the output of the function, meaning the first term is 5. So if we were to list out our sequence, the first term was 5. And maybe the second term could be 8, okay? And maybe the 23rd, or maybe the, why did I put A23? I meant to put A3. So the third term, maybe we'll call that, I don't know, 11. And all of a sudden you see a pattern stemming. Well, like I said, an is the name of our sequence, so we would write that as an equals 5, 8, 11, and so on and so forth, following that pattern, okay? Or we can say literally the first term is 5, the second term is 8, the third term is 11. So notice our inputs are the term number that we're at, or the n value, okay? The 1, 2, 3, 4, 5, etc. And our outputs are the actual values of our sequence. Now, this specific sequence is called an arithmetic sequence, but we're going to get to that in a second. Everyone take a look at this sequence. 5, 7, 1. So the sequence itself is 5, 7, 1, 2, 8, 3. Nothing impressive about that sequence. In fact, we can't even predict that sequence or use any type of pattern regarding that sequence. Okay? There's nothing special about this. However, we do know A1 is 5, A2 is 7, A5 is 8, right? The fifth term, 1, 2, 3, 4. The fifth term is 8. Okay, so here we have input is the term number, output is the value. Input, second input, output, etc., etc. Okay? There's no pattern here. I could not predict, if I wanted to, what the 11th term is. I can't predict it. When we have arithmetic sequences, though, we are able to predict it. This is an example of an arithmetic sequence, and I'm about to tell you why. By the way, here, it's spelled like the word arithmetic, but it's pronounced arithmetic. Okay? This arithmetic sequence has a common difference, or D. So this is actually a different sequence, but it's still arithmetic. It's pretty close to the other one. Actually, you know what? I'll just erase this first term. Boom. Now we have the same sequence we were dealing with over here, right? 5, 8, 11. I'll just start it there. 5, 8, 11, 14, and so forth. Notice that the common difference is 3. And our common difference is basically what are we adding from one term to the next. So we're always adding a common difference from term to term to term, okay? So for example here, we're adding 3 every single time. So now I actually could predict what the 7th term in my sequence is, because I know the 1st, the 2nd, the 3rd, the 4th. I can plug in the 5th by adding 3. I can plug in the 6th by adding 3. And then I can plug in the 7th by adding 3. And boom, all of a sudden I know what the 7th term is. 1, 2, 3, 4, 5, 6, boom. The 7th term is 23. And this actually directly leads us into how we would write a recursive rule for a sequence. Because the recursive rule tells us how to get from one term to the next to the next. Well, with a arithmetic sequence, it's very easy to go from term to term to term because we're just adding the common difference, okay? So let's identify, are they arithmetic or not? Why don't you take a couple seconds to see, is there a common difference for each of these separate 3 arithmetic or not arithmetic sequences? All right, you should be back with me because you probably should have hit pause. Notice you're adding 2 for each of these. So is this is this an arithmetic sequence? Yes, because there's a common difference of 2. So if we have the common difference, then we identify clearly it is an arithmetic sequence. Okay, is this one an arithmetic sequence? We subtract 7 again, subtract 7 again. Yes, it is arithmetic. Now, we would not ever classify this technically as subtracting 7. That's not how we deal with arithmetic sequences. We would deal with this as adding a negative 7. So common difference is negative 7. We are adding a negative 7. What about this third one? Whoa, my screen just jacked up. What else is new? Gotta love the technology. Okay, so plus 4, plus 2, plus 4, plus 4. Almost arithmetic, but it's not. There's one term that's off. Because we are not adding something every single time that is common, right? We're adding 4 most of the time, but here we only added 2. This is not an arithmetic sequence anymore. It doesn't go up by a constant rate of change. You're going to start to see why we're doing arithmetic sequences now. We're looking at arithmetic sequences because they fit into our linear functions unit, because they model linear functions as they're going up by a common rate, by a common difference each time, or a identical rate, right? A constant rate. If this was a graph, 1 would be our input variable value, and then our first value in our sequence. 2 would be our next one, and then it would go up some common difference. 3 would be our next value, and it would go up another common difference, where that jump is always the same jump. Now, this is the shape of a line, but it is not actually a line because we don't actually have any points in between this, since all we have in our sequence are our heights, going back to our initial sequence that we had, 5, 8, 11, right? Remember that sequence? 5, 8, 11, etc. Where this was our first term, second term, third term. Now you're starting to see why this fits into the linear functions scenario, because it goes up by a constant rate of change, because it's actually going up by a common difference every single time. So is this one arithmetic? Nope. So now we're going to get into writing a rule for this. Because sometimes, yeah, it's awesome to list it all out, but that takes a while if we want to go to like the 20th term, right? So what we start doing is writing rules, just like we do equations, for our arithmetic sequence. So on the recursive rule, there are 2 things that are important. The first thing you have to do is state RA1. That is the first thing you must do. Okay, the second thing that you must do is state how to find any term based on the previous term. I put that in quotations for a specific reason, okay? Because we're actually going to have a concept replace the words any term, just like we're going to have a different concept replace the word previous term, or the words previous term. Highlight those as you put this in your notes. So step number 1, we are going to state what A1 equals. Step number 2, we are stating how to find any term based on the previous term. And this terminology is really important, okay? In fact, I hope that it's like 10:30 in the video. I hope that you guys rewind back to that moment, 10 minutes and 30 seconds into this video, in a couple minutes after we get to the next slide or so. It might be good to rewatch this scenario play out. All right, so any term. Oh, don't you guys remember from earlier in the slides, I said AN, not only does it name the sequence like what we've been doing, right, where we name it out in front, just like f of x, but now it's AN. So it names it, but it also means any term. So we're going to actually have AN as a part of our equation in the recursive rule. Right? Because here in the recursive rule, we're stating how to find AN, any term, based on the previous term. So any term is AN. Similarly, we can state what the previous term's name is, and the previous term is A subscript n minus 1. This is not AN and then minus 1 where the 1 is big. It's like a whole number. That's not what we're saying. We're saying the subscript is now n minus 1. So A subscript n minus 1. That symbol, so this symbol represents the word's previous term. This symbol represents the word any term. And remember, we're trying to write something that tells us how to find any term based on the previous term. Well, look what we're doing. I'm taking a term and I'm adding the common difference of 2. Adding the common difference of 2 again. From any term, how did I get there? Well, I went to the previous term and added the common difference. Do you guys agree with that? If I want to find this term right here, one way of doing so is to go to the previous term, 3, and add the common difference. That is super useful because if I want to find this term right here that I don't know, I go to the previous term, which I do know, and I add the common difference. This is pretty baller. So if I want to find any term based on the previous term, I'm really saying for any term, it's going to equal the previous term. Hold on. Got to give myself a little bit more space. Any term equals the previous term plus the common difference. You guys agree with that? If I want to find the 7th term, I know it's the 6th term plus the common difference. Well, what is this? AN equals AN minus 1 plus our common difference. That is the second part of our recursive rule. So I'm just going to copy that right here. So we're going to state what A1 equals, and then we're going to state AN equals AN minus 1 plus our common difference. Let me get some of this out of the way. So you have to have this stated, and then you're stating this. Because you need to know a starting point, and then you're saying from that starting point, just keep adding this value, right? So we're basically saying, how much are we jumping from point to point to point? And then we're saying, okay, go all the way back to the beginning. Where was that first initial point? And as long as you know the initial point and how much we're jumping by, we know the whole sequence. Here's an example of that. So this would be an example of a recursive rule. A1 equals 7. AN equals AN minus 1 plus 5. This is a fully written out recursive rule. Because if you notice, I have written the first term, I've stated it, and I have stated also what the any term is based on the previous term. here we're saying the first term is 7. Any term thereafter is the previous term plus 5. So I've done my two things. Stated what A1 is, check. Stated how to find any term based on the previous term, okay? Any term is 5 more than the previous term. Now we know what the common difference is. So from this information, I could actually list out the entire sequence. I know what the first term is, and I know what the common difference is. It's 5. So I'm just adding 5, add 5, add 5, add 5, etc., etc. Okay? Boom. From the rule, you can create the sequence. From the sequence, you should be able to create the rule. So once again, any term is an, previous term is an minus 1. That makes sense because if a6 is our term, then the previous term is a5 because it's n minus 1. N was 6, right? An is 6. An is a6, sorry. N is 6. Then we've got an minus 1 is a5. So we're saying, we could really say, if I need to know the sixth term, so 1, 2, 3, 4, 5, if I need to know the sixth term right there, I go to the fifth term and I add the common difference. And boom, that takes me to the sixth term. That's what a recursive rule does for us. Okay, so remember how I said I was going to move you guys back in the slide? Go back right now to 10 minutes and 30 seconds into this video and rewatch this. So there's about 6 minutes now that you need to rewatch. Go ahead and do that, okay? All right, you're back. Hopefully you just rewatched that 6 minutes a second time, and now you're back for moving on. All right, let's take a look at, oh, we already did this. No, let's take a look at this, and let's write the recursive rule. Okay, so step 1, state what A1 is. A1 is 5. Step number 2, tell us what AN is based on AN minus 1. That's what we're doing every time. AN is based on AN minus 1, increasing by 3. We are adding 3 each time because we have a common difference of 3. And so we're saying start at 5, add 3 every time. And that's how we write our recursive rule. Boom, that's it. Here we go. Start at 27. That's what that's saying. And for any term after that, all we need to do is know the previous term, and then we're going to, it looks like, add -5. So subtract 5. Okay? So this is our recursive rule for this scenario. Start at 27 and decrease it by 5 each time. Okay? Yeah, that's it. Hopefully this video has helped you guys learn about arithmetic sequences and the recursive rule. Thanks, guys.